It's the wrong one. Are you guys seeing anything right now?
Yeah, I can.
The slide?
Yeah, I can see the slide.
Okay, awesome. All right, I guess let's get started. All right, so today I will be presenting on how to forecast financial crashes using quantum computing. So even though economics is not an exact science, there exists theoretical analysis which can, in principle, quantify and model certain processes in the financial markets, like physical laws do for the universe. And if we follow this idea, quantitative finance and economics will emerge. And these will apply to understand the evolution of financial markets and economies, as well as to forecast their foreseeable future. A realistic question in risk management is, would there be a drastic drop in market values if the price of assets suffers some small perturbation? The cross-holdings and non-linear character of financial network dynamics will cause chain reactions, implying that sudden drop of a market value might affect other nodes in the network, resulting in a financial crisis, which is pretty much like what happened back in 2008. And presently, the prediction of crashes is mainly performed by studying previous cases in history. So, people in 2008 will study like what happened in 1932 or other stock market crises. But those previous cases are pretty scarce. And if we compare with the current configuration, this empirical approach would only be semi-successful because the economic environment is constantly evolving. Hence, we cannot limit ourselves to predicting economic disasters solely based on historic data, and we need to figure out something new for this. It has the slide changed? Okay. Whoops. So there are two key questions that we need to ask ourselves. Imagine a financial network where institutions hold a number of assets as well as part of the other institutions in the network. So each of the institutions are kind of correlated with the assets and the other institutions. And that's actually what's going to cause the chain reaction. Well, now we need to ask, could a small change in asset value cause a massive drop in the market value of the institutions? Or in other words, could there be a financial crash? So mathematically, the problem of forecasting a crash is intractable. The author shows that if we would like to calculate the number of institutions that can fail in a network is actually NP hard. In particular, the author showed that it is as hard as calculating the maximum balance clique in a bipartite graph. And that is known to be an NP hard problem. And also there are evidence showing that it's even hard to get a good approximate solution. And I'm not gonna dive into the details of proving that predicting number of institutions that can fail in the network is NP hard, mostly because I didn't really understand what the author was trying to prove in that paper as well, but we should just take it as granted for now. It does seem like a pretty hard problem. And so the author also provides some stats regarding the classical runtime. So even given complete knowledge of all the assets and cross holdings in a simple network of around 20 to 30 institutions, it would take more time than the age of universe to compute the effect of perturbation. So now we need to formulate the problem in a conceptual level. And this point is still not connected to quantum, but we will get to it. So in this model, we have a network of institutions. And in this case, we have N institutions as well as N assets. And institutions could be countries, banks, companies, etc. Whereas an asset is any object or project with an intrinsic value. So like stocks, bonds, options. And financial institutions can own shares of the underlying assets. Moreover, there are also interdependencies between institutions modeled by linear dependencies. And such cross-holdings model the fact that some institutions may own share of other institutions, as well as approximate debt contracts between institutions. So like, Goldman Sachs might own like shares from JP Morgan, etc. Now let's recap on the list of variables that we would need for this model to work. The first one's N, the number of institutions, and then M, number of assets. And PK stands for the price of asset K. And DIK means institution I owns DIK shares of asset K. And CAB means that institution A owns CAB shares of institution B. And we know that CAA, which is kind of the self-ownership of the institution, is 0 here. It doesn't really make sense, but I will explain that later on why the self-ownership is CAA is 0. And then we have another variable specifically for the self-ownership of institution, and that is denoted by O tilde I. And for the last two rows, we have the equity value of institution I and the market value of institution I. Regarding what those two variables stand for, I will dive into details later. So this is the first variable that we're going to discuss, the self-ownership of institution I. And we can see that equals to 1 minus a summation across all of the institutions of their CIJ. And remember that CIJ is institutions I's ownership of institution J. So this summation essentially subtracts out all of the external ownership from other institutions, which means that you're left with the share of yourself. Does that make sense? And the second formula is for calculating the equity value of institution I. The first part is the equity value of the asset it owns. And the second part is the equity value of other institutions that it owns. So for the first part, it sums across all of the asset universe, which there are M assets in our universe. And you will be just multiplying by the number of shares with the price of the asset. And in the second summation, we will sum across all of the institutions because we may own a stake in all of them. And the CIJ is the stake that you own in institution J, and that's multiplied by the equity value of institution J. So the summation of these two summations will give us the equity value of institution I. And this explains why we let the CAA equal to 0, because mathematically it's a lot simpler to just sum across all of the institution in the second summation. Otherwise, we will have to say, I cannot equal to J in the second summation. And another interesting that we should note is that the equity evaluation significantly overvalues the institution. In particular, we can see that the equity value of institution I is in the total value of the institution in the system will be much larger than the total value of the underlying asset. And you can just observe that because the underlying value of the asset is simply only the first part of the equity value formula. And this occurs because each asset not only count towards the equity value of the institution that owns it, but also to the institutions that have an equity stake in the asset's owner, which is the second part. So the network's inflation of equity value is actually well known and validated both theoretically and empirically. Additionally, we have the formula for the market value of institution I, which is discounted by its self-ownership of its equity value. And now let's put everything together in a matrix vector form for simplicity. So for the self-ownership, remember, it was just like 1 minus all of the external shares by the other institutions. So we're going to turn this into a diagonal matrix where the diagonal elements are just going to be the self-ownership of each of the institution I. And for the equity value, if we look at the first part, this is conveniently written in a matrix vector product. And it's going to be D dot P. And the second part is going to be the matrix C dotted with the EV of all of the other institutions. And if we just rewrite, if we just like put C dot EV to the left side, and we're going to get EV equals to I minus C inverse times the matrix vector product of D and P. And note that the D is the asset ownership matrix, like how many shares of asset does each institution own, and the P stands for the price vector of all of the assets. And for the market value matrix, for the market value vector, we simply have the self-ownership dotted with the equity value dotted with the equity value vector. So again, to review, there are the O is a diagonal is a diagonal matrix containing the self-ownership of each institution, and the equity value is a vector for each of institution, and MV is the market value vector discounted by the self-ownership. Okay, so now you're thinking that I'm only really seeing how we structure this normal market, and where does the market even fail, right? We haven't built that into the model. So as explained in the paper, the model further introduces the notion of failure. This means that if the market value of an institution drops below a certain critical threshold, then the institution will suffer an extra discontinuous loss in equity value. This nonlinear behavior models the fact that if an institution cannot pay its own operating costs, then it may see a sudden drop in revenues. And moreover, if confidence in the institution is downgraded, then it may also see a sudden drop in its value, since it will be more difficult to attract investors. And mathematically, this is modeled by a step function, such that if the market value VI of institution I drops below a critical threshold, then it incurs a failure, and then its equity value drops by an additional beta. So we can define this B function to account for the general case. And this nonlinearity is actually what makes it extremely difficult for classical computers to determine if the market values of institutions after a small perturbation in the price of assets will behave. And specifically, given an equilibrium which satisfies this equation, the sum of all assets price drop by D, then it is NP hard to determine the maximum number of failures that could happen once the new equilibrium is reached. And NP hard in quantum computing kind of stands for no problem if you know how to structure this into an optimization problem. So now that we are given the mathematical formulation of this market failure, we recognize that this is an optimization problem. So how do we map it to quantum? Okay, to just making sure, are people okay with the these formulas on the slide, on this current slide?
Yeah, could you just reiterate, sorry, the bottom two formulas?
For sure. So the H, the squiggly H thing is a heap size step function. So you can essentially see that if the market value is larger than the threshold, which is MVIC, it's going to be 1 by the heap size step function, which means the beta P is going to times 0, right? And in that scenario, with the BI, which is the punishment of market, is going to be 0, because your market value is higher than the threshold. But in the case when your market value is lower than the threshold, in which case MVI will be smaller than MVIC, the heap size will be 0, which means the BI will equal to beta P. And in that case, you will suffer a loss in beta P, because if you look at the last formula on the slide, MV equals to the O tilde matrix times the inverse, and the DP will be subtracted by the B value, right? And I know that there's kind of jump between the second to last formula and the last formula. It's the only difference between those two is that the second to last formula is written for each of the elements in B, and the last formula is written as a vector form. Cool?
Yeah.
Awesome. Okay, so the answer to most of the optimization in quantum is simply QUBO, QUBO, QUBO. And QUBO stands for quadratically unconstrained binary problems, and it can be efficiently optimized on D-wave machines using quantum annealing techniques. So first we have to figure out the problem that we are trying to optimize on D-wave, right? If we look at the equilibrium definition of the market value has to satisfy the first formula. And if the market value vector satisfies the first formula, then we say that the market is at equilibrium, because this is how we derived it at equilibrium. But if we perturb the market, the MV, the market value, might not satisfy the equilibrium formula, and we can quantify the amount of perturbation by subtracting it with the market value at equilibrium. And the market value equilibrium is calculated by simply plugging in the market value to the right-hand side of the equation listed at equilibrium, because that will produce, what would the market value be if it were at equilibrium. So subtracting market value and the equilibrium market value will give us the perturbation of the market. Well, the problem with this formulation is that there's no quadratic terms in it. So we need to figure out a way to map it to a cubical problem, which is quadratic. So we need to do something about that. And it's pretty simple. You just square it, and that's going to give you some really neat quadratic terms. So the above expression is strictly larger than 0 away from equilibrium and equal to 0, and therefore minimum at equilibrium. So therefore, we have recast the problem of finding the market value in equilibrium as a variational problem. We're essentially trying to find the vector market value at equilibrium, and that will be the one that minimizes the classical cost function for a given network configuration. So now we've secured two elements of quantum annealing, which is a quadratic and constrained problem, and the solution would be its minimum energy level. So now we know that the market value vectors is the solution we are seeking to obtain. How do we map it to qubits, right? And market value doesn't have to be integers, but do remember that in C191, I think when we're deriving like the quantum FFT, we use qubit to represent floats. And so we can do that to the market value and encode it in the same way. So essentially, this is the xik will be the binary variables, and the 2 to the power of k, which ranges from -q to q, will simply represent decimals if k is smaller than 0, and represent integers when k is larger or equal than 0. So next, we need a procedure to deal with the failure term, the B function, because these are highly nonlinear and modeled by the Heaviside unit step function, and that is discontinuous. So in order to obtain an appropriate Hamiltonian for a quantum annealer, it would be desirable to have a continuous function instead. Moreover, we will need a Hamiltonian that can be efficiently described, even if it has many qubit interactions. So under these constraints, we need to find a way to approximate the Hamiltonian using continuous function. And we can do that by approximating the Heaviside function using a polynomial expansion. And if we look at the second equation, we essentially, we kind of mask which polynomial approximation that we're using, because there could be multiple options like Legendre, Taylor expansion. All of those can be useful. So in a case for simplicity, we're just rewriting the second part as a polynomial expansion with degree r. Okay, and this approximation makes the failure term much easier to handle for our purposes, while still being strongly nonlinear, because now it's nonlinear, but it's also continuous. Okay, so the only thing left for us to do right now is to find the Hamiltonian. So let's first recap on the approximation we've made so far and how we're mapping the market value to bit representation. So the first formula on the slide is how we're mapping market value to bit representation and keeping it as a float. And the second formula is essentially how we approximated the discontinuous function of Heaviside, but also making it, retaining the nonlinearity nonlinearity present inherent within the market. So now the author has a specific qubit in mind. We actually use the poly Z qubit, and then we can define the quantum Hamiltonian by promoting the classical bit variables, which is xik, into diagonal qubit operators with eigenvalues 0 or 1. And in terms of spin 1/2 poly operators, that can be just written as x equal to 1 plus poly Z divided by 2. It's a 2x2 matrices, and the eigenvalues will be 0 and 1. So with the approximation of polynomial R, we realize that a Hamiltonian is going to be of degree 2R, right? Because the BI function is in the expression of the MV equilibrium. Let me remind you. So in the MV equilibrium formula, where is it? You can see the B function, right? The B vector. And in that B vector, we use the Heaviside step function, which is approximated by a degree R polynomial, right? So when we plug that in to our approximated Hamiltonian, it's going to be degree 2R because we also square the perturbation. All right. So you might be asking, what does degree 2R Hamiltonian mean, even fundamentally, right? It essentially means that each term in the Hamiltonian involves many qubit interactions for different sets of qubits. And these interactions can range from 0 qubit terms up to 2R qubit terms at most. Okay. Any question at this point? All right, let's keep going. So there is a problem with polynomial degree of 2R for Hamiltonian. So remember that we are doing a cubal problem, right? And that Q stands for specifically quadratic. And the 2R degree polynomial is not going to cut it because it's much larger than a quadratic. So the Hamiltonian equation A could already be used as an input for quantum annealer if that quantum annealer allowed for multi-qubit interactions. But however, state-of-art quantum processors target, for practical reasons, Hamiltonian with at most 2 qubit interactions, which falls into the category of quadratic unconstrained binary optimization problems. So mathematically, finding the ground state of such Hamiltonians amount to solving qubit problems. And in our case, it would then be desirable to have a Hamiltonian made of at most 2 qubit interactions. So therefore, the final step of our derivation is to bring the interactions in Hamiltonian down to the 2 qubit terms at most. And it turns out that there is a technique which allows us to implement efficient k qubit interactions using k extra ancilla qubits and end up with a 2 qubit interaction only Hamiltonian. And note that we are not trying to replicate the exact Hamiltonian because we're only interested in a ground state that corresponds to the equilibrium of the financial market. So the trick is essentially to rewrite another Hamiltonian made of at most 2 qubit interactions such that it reproduces the low energy spectrum of our original 2R degree Hamiltonian. Okay, just to recap, we are trying to find a 2 degree Hamiltonian so that its low energy spectrum is going to be identical to our 2R degree Hamiltonian. And in that case, that would be good enough for our problem. So how do we do it? So the topology of interaction for a toy case, we can look at on the right. For the case of 4 qubit interaction proportional to poly Z, poly 2, poly Z3, poly Z4, qubits on the left are the logical qubits, and those on the right-hand side are the ancilla qubits. And essentially the method is saying that if you have a 4 qubit interaction, you will be able to find a 2 qubit interaction Hamiltonian with identical low energy spectrum if you are using 4 ancilla qubits, or ancilla just mean extra qubits. And the topology of the interaction is shown there such that all of the larger qubits are coupled among themselves via a 2 body interactions with strength J, and each ancilla or extra qubits are coupled to every larger qubits with 2 body interactions of strength JA. And moreover, there are magnetic fields H and HA accounting for 1 qubit terms. So the idea, as explained in the paper that the author linked to, is to find the values of J, JA, H, and HI such that the low energy spectrum of 2 qubit interactive Hamiltonian reproduces the energy spectrum of k qubit Hamiltonian. And this is achieved by the choice listed on the lower left corner of the slide. The derivation is very complicated, so let's skip it for the sake of this presentation. So essentially, the low energy sector of the Hamiltonian in equation 10 with coupling will reproduce the spectrum of a Hamiltonian with degree 2R up to an overall additive energy constant. And this is guaranteed for the part of the spectrum satisfying certain conditions and allows the annealer to sample over low energy states, effectively reproducing the energy landscape of the many qubit interactions on logical qubits. So although we don't really need to worry about running out of qubits for a toy case problems on D-Wave, which have a ton of qubits, but it is still good to practice our resource estimation skill. Essentially, we're trying to ask ourselves, how many qubits do we actually need for this problem, right? And what's our limitation? So let us now consider how many qubits we need. First, we would need 2q plus 1 qubits because that's how many qubits we're taking to represent each market value as a float, right? And amounting to a total cost of logical qubits of n times 2q plus 1 because we have n institutions which each have one market value. Okay, and another aspect that we need to take into account is the degree 2r Hamiltonian. So for each degree from 0 to 2r interaction, we need a separate ancilla qubits to take care of that. So if we look at the n terms formula on the right, it essentially is saying that the 2r degree Hamiltonian is going to have all of the interactions from 0 to 2r qubits. And remember the theorem that we just talked about there, that there is a technique where you can use n qubits and extra qubits to rewrite a Hamiltonian into 2-qubit Hamiltonians if you're having n qubit interaction. So the combination is essentially saying that we have n times 2q plus 1 qubits already, but then we need to figure out how many ways can they interact from power of 0, power of 1, all the way to power of 2r. Okay, is that intuitive for everyone? All right, seems not a lot of question. So if we sum that up, that's going to give us how many extra ancilla bits that we would need for this problem. And we can actually further simplify it by making the following assumptions. So for nq much larger than r, and the leading term of the equation on the right is actually the binomial coefficient for alpha equals to 2r. And so for n times 2q1 much larger than 2r, together with 2nq much larger than n, we can use approximation of like 2r factorial is larger than 2r divided by e. And we have, and we will be able to rewrite that equation from the on the right to this current equation. So therefore, the number of terms to specify the Hamiltonian is a polynomial in n and q, whose degree is controlled by r, right? So we're not done here. Because if we allow an additional degree of freedom for r, this means that total number of qubits will need to be multiplied by r. So to compare with the classical method, the problem is NP hard for any r larger or equal than 2. And the author is saying that their derivation shows that it is as hard as finding the ground state of an arbitrary spin glass problem. But the thing is, although it's very nice that we are able to get this resource estimation done, but note the cost of mapping from a k-body Hamiltonian to a two-body interactive Hamiltonian, because most of the overhead for resource comes from the ancilla terms, right? And another research paper found that an effective 2-qubit quantum Hamiltonian could still not be readily directly into the D-wave system, which requires qubit type input or an Ising type input, even though some open source software like PyQubit can generate it, the input size must be very small in order to avoid a stack overflow associated with the recursion errors. So once we generate the input for this problem, this is still too large to be embedded in D-Wave 2000 quantum annealer because of the graph structure. So the current workaround proposed in the paper is using QBSolve. And D-Wave provides a software named QBSolve that allows us to combine the power of classical computer with its quantum annealer, which is in a way hybrid. And how it does that is by splitting up the qubit matrix into partition matrices that can be embedded in a quantum annealer if they're small enough. And as a decomposing solver, it finds a minimum value of large qubit problem by splitting it into pieces solved either by D-Wave system or a classical tabular solver. And both approaches were considered here for compression purposes. So instead of a real quantum annealing process for the entire qubit matrix, QBSolve actually provides a tabular algorithm or D-Wave annealer for some matrices. The partition strategy for generating submatrices may get stuck in a local minimum instead of the global minimum that the quantum annealing guarantees. So considering that the larger qubits only encode less than 1% in the qubit matrix, because remember, a lot of the overhead, a lot of the extra qubits are coming from the mapping from a high degree Hamiltonian to 2-degree Hamiltonian. So the actual larger qubits only encode less than 1% of the cubic matrix, right? So the risk of getting stuck is pretty high. And the author also ran a number of numerical experiments. So they generated a random financial network with 10 institutions with a minimum self-ownership of 0.50%, as well as 20 assets with prices ranging from 0 to 100. And then they perturb the network by subtracting a random vector from the asset prices. And this perturbation has a maximum amplitude from 0 to 80. And they then looked at the number of failures of institutions as a function of the perturbation amplitude. So, the graph on the right shows an example of a random financial network with 10 institutions, and the dot corresponds to institutions and links to the cross holdings. The amount of cross holdings correspond to the thickness of the link. So for the perturbation experiment that the authors ran, they found that the number of failures depend on the perturbation as shown in a figure on the right. And they clearly see the phase transition from the normal to the crash phase in the figure. When the perturbation amplitude is around 60, basically all 10 institutions in the financial market fail, which means that their market value drops to 0. And notice that the region where the crash happens is very small, roughly for the perturbation amplitude between 55 and 62, right? You can see like there's a very narrow region where all of the institutions, where from no institution is failing quickly to a institution or 9 institutions failing. So following standard condensed matter arguments, the amplitude of the region is expected to shrink as the number of institutions grows, which makes sense because the opportunity window of all of the institutions failing is going to be much more trivial, trivialized if there are a lot of players in the market. So thus making the transition sharper and therefore making a prediction of the crash after small perturbation will be even harder if the number of institutions is growing. And so seems like I went too fast again. And so here's the reference. If you're really interested, you can read these following three papers. The first one is where I based this presentation off of. And the second one is sort of the classical way of people are evaluating sensitivity and the complexity in financial networks. It is also how the authors derived the initial problem formulation with all of the matrices and vectors. And the third one is actually using a D-wave quantum computer and use workarounds to make sure that the problems, even a toy-sized problem, can run efficiently on a D-wave machine. All right, let's open up to the floor.
I might have missed it. Could you explain the definition for perturbation?
Yeah. So the perturbation is essentially saying that if we apply a tiny amount of changes to the asset prices, and we're trying to see how many institutions would fail afterwards.
So just, is there a definition for how big that asset change is going to be?
Yeah. So as you can see in the experiment that the authors ran, the prices originally should be like from 0 to 100, right? But their perturbations are actually pretty large. It's like from anywhere from 0 to 80. And they only really find meaningful results when the perturbation is 60, which is like 60% of price changes, which is exactly not a tiny perturbation. So I guess they didn't really keep their words by having a small perturbation. Yeah.
And also I was wondering, why does that failure all of a sudden like goes from the top to the bottom again? At these points, like just why?
The author is saying that there is like a physical reason, like they're saying that if you follow standard like finite size scaling, I'm not sure what that is, but they're saying that it's either that physics is affecting how D-Wave is running their simulation, or there's like some fundamental connection between the structure of their conceptual model of the market is related with say the D-Wave mapping, like how their lattices is designed. And because of that correlation, they're saying that the amplitude of this region is going to shrink if number of institutions grows. They didn't really give a clear reason of why that is happening. It's very counterintuitive. Like, if the price disturbed like by more than 60%, why would none of the institutions fail, right? So they didn't give a clear explanation for why that's happening.
But in that sense, it wasn't a simulation error. It's rather a underlying phenomenon.
Yeah. I don't think it's a simulation error. It could be a simulation error if they didn't sample it correctly. But but this doesn't look, statistically
I see.
trivial. Yeah.
Okay. Well, thanks.
So I was wondering, sort of on that same basis about like when this amount of perturbation results in a large number of failures. So that MVIC term, could you just explain again, like how we're choosing that that threshold term?
Oh, the MIC term?
Yeah.
I think in their case, it's kind of arbitrary. They set it to what did they set it to? They set it to 0.8% of the original of
So
their
it's like
market value.
hard-coded in.
Yeah. So obviously, this is going to be a very idealized model. Like their market value, it's not like all of the hedge funds. They don't have like they have like their separate like risk management departments. So and this is in this model we're assuming that if the market price if the market value of your institution reaches that threshold, everything is going to go to hell. But that's not exactly what happens in real life.
Right.
Yeah.
So like if we were to pick some subset of institutions in real life and have all the relevant data, then how would we I guess determine that threshold, or would that not, or is that not really feasible?
I guess from the top of my mind, it would have to you would have to add like a risk coefficient to and weigh that with the asset prices, because maybe depending on what kind of institution you are, maybe if you are facing if you are some type of institution that can be severely affected by your partners or by external investors, like you might not want to perform certain actions, but they might force you to do it. So in that case, your essentially your commitment to the threshold price is much stronger than the other institutions that have more freedom in terms of their own investing.
Okay. And sorry, just one more question. So the paper was mentioning that as the number of institutions grows, the transition becomes sharper. So would that mean like, so if we had like a relatively low number of institutions, would there be like more degrees of how bad the failure is? Whereas like if there's a large number of institutions and they hit the threshold, then it becomes very bad very quickly.
Sorry, could you repeat that again?
Yeah. Okay. So if we have like a relatively small number of institutions, does that mean that once we hit that threshold, the degree of failure sort of increases slowly as it goes farther below the threshold, and then
I see what you're asking. Yeah. So they didn't really say. Okay, so yeah, so they didn't. Maybe I should rephrase. So they didn't say that the amplitude, which is the height of spike, might shrink as the number of institutions grows. They're saying that essentially the opportunity window for institutions to fail might shrink. So you may still reach the same number of failures. So if you have like 4 institutions, if you are failing 8 out of 10, maybe you can still fail 3 out of 4. So the height of the spike isn't what the author is trying to say. Isn't what the author is saying will decrease. They're saying that essentially the width of the spike is decreasing.
Oh, okay.
Yeah. But as Andrew just asked, like, why is there even a width? It should just be a curve leveling off and everything goes to hell, right?
Yeah.
So that's a very interesting question, and I was gonna do a D-wave experiment on it, but I have a datathon this week, so I couldn't really I didn't have the time to do it. But this could be a cool simulation to run.
I see.
Could you go back to the previous slide where you have the order
formulas?
of here. Where in the second line the order is r times that blob. Where does
Yeah.
that extra r
Okay.
come?
Yeah, gotcha. So they're saying, so if we don't assign r as a variable, if we're saying, we're going to keep the r fixed, then we don't have this r. But they're saying that, if you want to have like a really generalized model, which means that which means that r is going to be an additional degree of freedom, then r will have to be counted towards the number of qubits required.
Cool. Yeah, I think that makes sense.
Any more questions? Okay, seems like we are all good. Yeah. All right. Damn, I really need to work on my timing, but gotta make it stretch 1 hour. It's pretty hard. I don't know how you're doing it, Samia. Okay. Yeah. So I'll make sure that we actually have enough materials to talk about next time. But this will be all I have for this week, and you guys, I guess we're free to go to our weekend times. All right, everybody. See you next week.
All right. See you guys then.
Thank you.
See you guys.